Well, welcome everybody. I'd like to thank Hyperion for inviting me to come and spend some time discussing in the next half an hour or so how we at Intel have been leveraging heterogeneity in the exascale era. And I'm also going to describe Aurora, which is the exascale machine to be delivered to Argonne, and show some of the critical steps that we are taking on that on our path to exascale. So let's start off by talking about what we mean when we say exascale. So, first of all, historically in HPC, we have focused on modeling and simulation, but that's changed in the last 5 years or more. Today, when we think about HPC, we really are thinking about all three of these pillars coming together. That is modeling and simulation, big data and analytics, as well as artificial intelligence and deep learning. When we think about assembling an HPC machine of the exascale era and going forward, we really are thinking that all of these type of workloads are coming together. And we'll talk a little bit more about that coming up. We all know, though, that sitting on top of this is the importance of data. Data has become extremely important in terms of how to move it around, how to be able to access it, and also how to visualize it so that we can understand what's going on. So let's take a look then and level set on the different trends that are affecting HPC. The first is heterogeneity. When you think about where HPC was, say, a decade and a half or 15 years ago to where it is now, what we found is the introduction of lots of different types of compute. So historically, there were just CPUs, but now there's CPUs, vectors, there's matrix engines, there's GPUs, there's spatial computation in the form of FPGAs. All of this has added a lot of complexity. But matching that on the software side of things as well, we see that that too has grown in terms of the different types of use cases that are being involved. We obviously know that there's the classic or the modeling and simulation HPC stack that we've been working with for the last couple decades, but there's also nowadays the artificial intelligence and the machine learning frameworks, the big data frameworks, and we'll talk a little bit about those in the future. And then finally, memory and I/O, those two are just expanding in terms of the different types of capabilities that are provided. So when we take a look at what's happened over the last 2 decades in HPC, heterogeneity, whether it's in the form of compute or software or the other aspects, memory and I/O, has really blossomed. It's in some sense it's a pro. It gives us the capability to get more compute per dollar, to give us more compute per power, but it also introduces some challenges that we'll talk about how to handle it. And in addition to that, new types of compute requirements have been introduced to HPC. So that includes the AI that we talked about, but also figuring out how to integrate and leverage cloud, make sure that we can utilize big data, and also get a lot of this data that's coming in from the edge. And the other thing as part of this is that AI and cloud are very, very large markets. And in some sense, they are driving some of the requirements. And so when we think about HPC, we need to take that into account as well. The net of it is that HPC today is more complex than ever. And there's some pretty fundamental shifts that have occurred and are continuing to occur. So let's look at one of those now. We've talked about this notion that HPC is no longer just about modeling and simulation, but HPC really is the convergence of modeling, simulation, high-performance data analytics, and AI. And today, there's many supercomputing sites, many HPC centers are doing a lot of good work in terms of figuring out how to combine and leverage these different pillars working together. But our vision is that we're only scratching the surface. Our vision is to not only to significantly widen the pipes, the arrows are representative of the rate at which data can flow between these pillars, but also to make it more productive, to be able to utilize code, technologies from all of these different pillars. There's some key technologies that we'll be talking about throughout this presentation that will allow us to achieve this. One of them is DAOs, one of them is a non-volatile memory, and another one is a different systems, a new system architecture that really focuses on data, that being the first class entity, and figuring out how we're going to connect all of these different types of pillars together effectively and tightly. So the other thing that's happening, and I've already mentioned this, is when we think about this convergence of AI/machine learning and HPC, what's really happening is modeling and simulation applications are benefiting from some of the AI capability and technology. And as AI grows and becomes and tries to incorporate larger and larger models, it needs to utilize HPC technology. So there's this mutually symbiotic relationship that's going on. And there's this notion of being able to use surrogates to significantly accelerate the amount of computation that effectively gets done for HPC workloads. And we're not talking about percentages or factors. We're talking about orders of magnitude. There's papers that show you can get 1,000, 10,000 times improvement in terms of being able to get a particular scientific output done. One just small example of this comes from the Princeton Fusion Lab. And I remember having conversations years ago with Bill Tang when he was beginning to take a look at this. And the interesting thing was, if it was a ground up, it was a zettascale type computation that we needed to do. And this was maybe a decade ago. And interestingly enough, as you see by what's on the screen, they got a Nature article out of this by incorporating some deep learning to control and to better understand when there's going to be escapes. So this is just one example of applying deep learning techniques into what would have been a traditional modeling and simulation application. And there's a lot of other analogous and other good work going on in terms of using surrogates, in terms of using deep learning techniques to really accelerate what we're doing in modeling and simulation. So let's talk a little bit more about Aurora and what we're doing on Aurora to bring a lot of these technologies to bear. So the first is this is a partnership between Intel, Argonne, and HPE. And what we are doing is delivering an exascale machine to Argonne to use, and it is indeed, like we talked about, it is a 3-pillar machine. We are focusing as a partnership on ensuring that all of these different types of technologies will be readily available and productively available on Aurora. But let's just talk about exascale and the type of computation that goes in. And, for the folks who've seen this, this may be a review, but it's sometimes really interesting to get your head around the true power of exascale computation. So the first is just how fast is how much computation really is an exascale. So the first is if all the humans on Earth, roughly 8 billion, spent plugging into your calculator. If you did a calculation every 10 seconds, right? So you do 1,240 times 123 or whatever. And if you did that every 10 seconds, it would take 40 years of everybody doing that to do what Aurora or an exascale computer will do in 1 second. There's a lot of stuff that goes into making this, 600 tons to be clear, of material. That's roughly the equivalent of a large airplane. And lots of networking, a very important aspect of this as well. So you can also see 300 miles of optical cables that are being used to wire up and connect these critical computing components. Lots of large data centers to take these machines into account. And I'm not going to say a lot more about this, but we do use liquid cooling to address the power and to address the efficiency of this. And then finally, data. I mentioned data, and we're going to come back and talk more about DAOs. But in 8 minutes, Aurora will be able to store enough characters to be able to write a stack of books that would stretch to the moon. So, it's pretty amazing when you think about the type of technology that we're bringing to bear. And just tying it into our last conversation as a reminder, we are doing this from a three-pillar perspective. So we will have the traditional modeling and simulation applications on Aurora, as well as AI, as well as high performance and big data. So taking a little bit more of a look from an architecture point of view, what you see depicted on the right is Aurora. The purple racks are not necessarily to count, but they are the compute racks. And then the orange and yellow racks are for holding the non-volatile memory, of which will be managed by Deos. Those go into compute cabinets that, as I mentioned, are water-cooled for efficiency. And in partnership with our subcontractor, HPE, it will be a dragonfly topology that connects all of these nodes together. Each of the compute blades in Aurora consists of a Xeon, a Sapphire plus HBM processor that we recently announced at ISC, as well as 6 GPUs, which are the Ponte Vecchio architecture. And these have also been announced utilizing Intel's 3D Foveros integration. So this is how the overall machine comes together. And then let's talk a little bit about the software. I'm going to go into both this slide and the next slide to describe the software of Aurora. So Aurora, as I just mentioned, on each blade will contain both a CPU and a GPU, right? So making our first steps into this heterogeneous environment. And so from a longer term perspective, how are we going to program heterogeneity, right? What has happened historically is for each type of compute, we've seen, until recently, we've seen different models coming up. I'm sure a lot of folks who are on this call are very familiar with Intel's OpenAPI software stack. This will be supported and will be in production on Aurora. We are partnering very closely with Argonne, as well as a lot of the other DOE labs, to make sure that it's meeting the needs of a lot of the key applications that are running, and that it will be a very broad ecosystem. But again, the goal behind OpenAPI as it relates to Aurora as well as heterogeneity is this notion that you write an application, you develop an application once, and then that code will run on a CPU, a GPU, or other engines, right? That's specifically to Aurora, but Intel does offer AI as well as FPGA engines. And so the code will be able to run on those as well. And if you're coming from an HPC perspective, it does support the standard programming languages that we use, C, C++, Fortran, as well as OpenMP, and as well as more modern programming languages such as DPC++, which is, if you're looking to convert from the proprietary CUDA format into something that's an open standard that will run across all platforms, a DPC++ is a really good choice to being able to do that. In addition to the programming models that I just talked about, much of the infrastructure, the developer tools, the developer libraries, the optimizations that you have, the debuggers, all of those that you're familiar with in what was historically Parallel Studio environment is also now available in OpenAPI libraries, and you see that depicted there on the right side of the slide. So while OpenAPI is already out there and available now for people to be able to use, it will be going into production and serving an important capability for Aurora. But it isn't just about developer tools, right? In order to get machines to scale, in order to be able to effectively leverage all this heterogeneity, we do need to have a set of core HPC components. And I'm going to talk about a few of those on this slide here. I've already mentioned OpenAPI, which is the first one. Another technology that we're putting into production on Aurora is something called MOS. And it stands for multi-OS. And this will be a capability that's available to Argonne and anybody logging into Aurora that has really high performance as well as scales. It is an operating system or a combination of operating systems based on a lightweight kernel, which has been traditionally shown in HPC to have high performance and scale really well, as well as a Linux kernel. Both of those kernels are run simultaneously on the same node at the same time. So you achieve the familiarity, the productivity of a Linux environment while allowing you to be able to achieve the high performance and scalability of a lightweight kernel. Another technology that we're bringing to bear is something called unified control system. These machines are obviously very large, right? Thousands, tens of thousands of nodes. And the ability to be able to control those machines effectively without a super large team, you need something called what we're dubbing a single pane of glass capability. And what this does is it gathers information from all of the different components of the system, whether it's the software, whether it's the nodes, whether it's the network, whether there's something going on with the memory, and it puts it into a single schema that's available both online, represented by that blue oval there, as well as stores it into a historical database so that users and or administrators can query after the fact and do cross checks about when their applications ran, how well they ran. Administrators can take a look at as hardware was replaced or was moved around, how that had an effect on availability and reliability. But it can be all done in a single context without having to go to different logs, the sys log or go to the job launch manager, whatever, to get the information. MPI, obviously an important part of the machine. We are continuing to, and we will provide an open source MPI. It will be optimized for the topology, for the Dragonfly topology, for the nodes that we talked about. Again, the 2 CPUs, 6 GPUs, and we will be also optimizing for the slingshot fabric capability. GOPM, power. Power, of course, is becoming more and more important on computers today. And GOPM is a job level power manager that allows you within a given power cap to be able to achieve improved performance, to be able to save energy when you're running jobs, right? And it's done on a job by job basis. And then finally on this slide is PIMX. This is the ability to launch jobs very, very quickly. And obviously an important thing on a system the size of Aurora. And Deos, I'm going to spend the next slide discussing. So let's move forward. We talked about data being a very critical aspect of running on these machines. And I told you about system architecture. One of the things that Aurora will have is sitting on the high performance fabric, it will have a massive amount of storage. And this storage will be managed by Deos. And what this effectively will look like then from each individual compute node is if you had non-volatile storage on your node. And the reason we can do that is because we leverage the significant bandwidth of the high performance fabric. And then Deos, by doing this disaggregation, now Deos can then provide that storage to any of the different compute nodes in the system. So let's talk a little bit more then about what Deos provides. Storage has changed over time. We all know that. People, by and large, are not using spinning disk for storage that's most readily and actively used by nodes. It's still oftentimes, of course, used for longer term storage and for massive data sets. But what we've done, as depicted on that previous slide, is to provide on the high performance fabric this non-volatile memory, the ability to very with high performance access data. Non-volatile memory has a couple characteristics that Deos has been designed for that spinning disks don't have. One, as we've already talked about, you have higher bandwidth to it. But two, you can also very effectively access smaller pieces of the data. And three, of course, you can randomly access it, unlike a spinning disk, which is constrained in terms of how the data is laid out. So Deos has been designed to operate in this type of environment. In addition to that, it also provides an object storage. And that plays, if you remember the original slide that we talked about when we were describing the ability to converge AI applications, that plays a very critical role in being able to productively move data. Because historically, when you wanted to move data between the different pillars, you had to linearize out through a file system, and then you had to read it back in. But by having an object storage, you can more productively just pass handles to the data around. So finally, when you think about all of the different system software, how are we going to integrate and really bring to reality that picture that was depicted back in the right in terms of having those wide arrows between? So in addition to the capabilities that Deos and the non-volatile memory bring, we also, and this is just an example, but we also need to figure out how to integrate these three different software stacks, right? The modeling and simulation, the big data analytics, as well as the AI and deep learning. And this is just an example from some other work that we're doing on Aurora to pull together Spark analytics and to integrate that more tightly into the environment. So the first thing that we're doing is we're partnering very closely with Argonne to more tightly integrate the resource manager within Spark to the overall system resource manager. And so this allows the overall system, the overall Aurora manager, to be able to understand the individual workloads that are being run on top of Spark. In addition to that, on a node basis, we are taking a look and we are making Spark aware of these richer and fatter nodes and making them aware of the fact that when you run a task in one portion of the node, it might not be the same as running it in another. And then we are also connecting up Spark with Deos to be able to, when you do the shuffles between each of the steps that's typically done in these applications, to be able to use Deos as a very effective and very efficient intermediate data storage when you're doing the shuffles. So this is just an example of one area where we are more deeply and more tightly integrating to bring to fruition this notion of being able to tightly couple each of these pillars. And finally, I should have mentioned this at the beginning, but Intel continues to be an active player in OpenHPC. All of the different software that I listed a couple of slides ago is being done in open source, and over time we are making contributions to OpenHPC. Some of them are already in, and over time others will go in. So, that depicts what we're doing from Aurora as an example, but where Intel is going in general, right? We talked about the key trends. We talked about the notion that AI, big data analytics, and simulation are converging. We took a look at OneAPI as well as some other software capabilities to allow us to bring this together. But let's talk about what's coming next, what's coming after Aurora as we move through the exascale era and we start thinking about the next era. So we talked about some of these trends. How are we at Intel addressing some of these trends? The first is there's an absolute recognition that we need to look at things from a systems perspective. Oftentimes, if you were to design an individual component and you're only optimizing for the component, you would reach one particular design point. But then when you go to put it in a system where it has to be balanced with other power, where it has to be cooled at certain ratios, what you find is, well, no, you want to operate at a different design point, or maybe you even need different capabilities. So whether it's memory, whether it's networking, whether it's cores, whether it's software, Intel is approaching designing HPC AI machines from an overall systems perspective. And we are absolutely leveraging the massive investments that we're making in cloud and AI, but we are focusing them on HPC. And in Ponte Vecchio, or PVC, the GPU that's going to be used in Aurora is a good example of that, where this was a really great computing engine, and in a good partnership and collaboration with Argonne, we made sure that it met the needs of future HPC type machines. And then we've talked about heterogeneous components and how important these are. It's going to be very critical as we move forward, and I'll spend the last slide or the next slide discussing a little bit more about this, to figure out how to bring all of these different types of heterogeneous components together in a tightly coupled manner and in a productive manner. And I'll say a little bit more on that in the next slide. We've already talked about the importance of having a programming model that encompasses whether it's CPUs, GPUs, FPGAs, upcoming AI engines, or there's mixed precision going in from the edge. And one API, again, is a productive environment where users can get familiar with a particular development environment and then apply the code that comes out of that to multiple different areas. And finally, we need to continue to focus on making sure that the platforms we're designing really do facilitate this ability to bring together HPC, AI, and big data. So then let's finish just with a little thought of where we're going for the future in heterogeneous computing. There's different levels that one can think about coupling heterogeneity. And over time, we as a community have looked at doing these differently. Intel has two amazing technologies that I'm sure you've heard about, both EMIB and Foveros, that allows us to much more tightly couple components. And then we also have introduced and are working jointly with a lot of industry partners to utilize CXL. So going forward, we envision a space where processors and accelerators, be them scalar, vector, spatial, or matrix, will be able to coexist much more tightly and much more productively to allow developers a lower barrier to entry to being able to access the power that accelerators are bringing to us. This heterogeneous environment, which allows greater compute per power and greater compute per cost, is an up-and-coming trend that we have addressed on Aurora as a first step, and we are continuing to move forward as we move through the exascale era to figure out how to bring these type of capabilities to the market, to customers, in a more productive and more performance manner. So finally, thank you. Aurora will be an exciting machine encompassing some of the important trends and directions that we are taking in exascale computing. It will indeed be a three-pillar machine combining the heterogeneity of CPUs and GPUs, as well as being able to combine modeling, simulation, AI, and high-performance data analytics in a productive manner that allows developers to more effectively be able to utilize the technologies that are coming. And this is just a first step on an exciting trend as we go through the exascale era and move into zettascale. So with that, I'd like to thank everybody for your time, and I hope you have a good rest of the user forum. Thank you.